And we're on. Ivy. So, extinction curves along the line of sight, the three lines of sight, the three stars. So this is as a function of wavelength, and so the idea is there's three stars, and so as a result there's different amounts of dust, different column densities along the lines of sights, which is why the curves are shifted from one another. It's 1 over lambda. Notice here's the U, B, and B photometric filters, so this is the visible part of the spectrum. Here's the bump due to graphite that I was talking about before, right? That's the bump in the absorption cross-section, so the bump in how much extinction there is. And then the other ones are off the curve, essentially. I don't think they fit on here, if I'm not mistaken. But in any case, there's the bump due to graphite, and then here's dashed lines are observed, and solid lines are computed, so clearly, we don't know exactly what is going on with the dust particles. In fact, we're still not sure exactly what they're made of, but one possibility, graphite and silicate grains ranging in size from 0.25 microns to a few angstroms, much smaller than that. The few angstroms would be the size of PAH molecules. So, so there's a range of sizes, is what it comes down to. And so, of course, this represents the composite effects of all the different dust particles in there. And it's important to remember that those dust particles' importance goes beyond just, they cause extinction between us and stars, because we live on a planet, it turns out, and terrestrial planets, probably even Jovians, although there's some thought that they might be able to sometimes condense directly out of the gas, but in the protostellar disk that surrounded the sun, which in the sun's case was called the protoplanetary disk, planets accrete, and the accretion process begins when little dust particles stick together, and then you go from dust speck size to little grain of sand size to big grain of sand size to pebble size to boulder size to kilometer big thing size to planet size along the road. So in other words, these interstellar dust grains become, when a star forms, the seeds from which planets can form around a star. So we like them because we're standing on something which exists because of the fact that the sun's nebula was seeded with dust grains. So the Earth is a huge collection of interstellar dust grains on some level, is what it comes down to. Okay, let's talk some more about the composition of the interstellar medium in general, since I already did all this stuff last time. So there is in the interstellar medium, the most prominent component is hydrogen gas, not surprisingly, right? Most of the ordinary matter in the universe consists of hydrogen. Some of the interstellar medium hydrogen is atomic, some of it is molecular. About 70% by mass of the ISM is hydrogen. About 9 out of 10 atoms is going to be hydrogen. ISM has H as its predominant component. About 70% by mass. H1, neutral hydrogen, is observed via 21 centimeter radiation. If I recall correctly, that's a frequency of about 1470 megahertz. And it originates from a spin flip transition. So in particular, the proton and the electron in the hydrogen atom can either have their spins aligned with one another or have them pointing in opposite directions to one another. And their spins give them magnetic dipole moments, which we're soon to talk about magnetic dipoles in E&M. But if you think semi-classically of a proton or an electron as a little spinning ball of charge, it constitutes, based on that, a circulating electric current. Currents give rise to magnetic fields, so protons and electrons have magnetic dipole moments associated with them, and they have an interaction energy as a result of them. The electron and the proton feel one another's magnetic fields, and it turns out that if their spins are parallel to one another, that has a slightly higher energy than if their spins are anti-parallel to one another. And guess what? The wavelength of the transition when the electron flips from having its spin aligned with the proton spin to opposite the proton spin corresponds to a wavelength of 21 centimeters. So that's what gives rise to this 21 centimeter radiation. It's not possible to observe it in the laboratory, and that's because this is a very low energy transition, and it's associated with a very long mean lifetime. Namely, about 11 million years is the average time it will take this transition to happen if you have an isolated hydrogen atom. In the laboratory, we cannot create a vacuum that's nearly as good as the vacuum of the interstellar medium, the near vacuum of the interstellar medium. And so, in any laboratory sample of atomic hydrogen, there's going to be a collision that causes the transition long before, you'll kick something up to a higher energy level and erase this, or whatever, long before or the collision itself can cause the transition, and the energy change will just show up in a slight change in the kinetic energy after the collision, as opposed to producing a photon. So you can't see this in the laboratory because the lifetime is too long compared to the mean time between collisions in any kind of laboratory gas. So,
so wouldn't they want to be like in a lower energy configuration?
Yeah, they would. They would.
So what would put them in the higher one?
A collision could do it. Or you absorb a photon, and then when you drop down to the ground state, you happen to drop into the slightly higher energy rather than the slightly lower energy. And because the energies are very similar to one another, the Boltzmann factor is not going to make a big difference. So about half the time you're going to drop into the higher energy configuration, and half the time you'll drop into the lower energy configuration. And then the half-lives I have like 11 million years. So it's going to take a long time before you would have everybody drop down into that configuration. So lifetime of upper state parallel spins about 11 million years. So we'll never see it in the lab as a collisional de-excitation will occur first. We'll never see it needing 21 centimeter radiation. So we'll never see 21 centimeter radiation in the lab. Since collisional de-excitation will happen first. In ISM, the collision time scale is typically a few hundred years in an H1 cloud, which is long enough that a little bit of 21 centimeter radiation is produced. Given how many hydrogen atoms we're talking about. This would, yes, I was gonna mention that. The wow signal was detected at 21 centimeters because, so first of all, often you're doing studies at 21 centimeters because you're trying to map interstellar H1 clouds. And so it just happened to be, you're often looking at that. But also, folks that do SETI deliberately often do it at 21 centimeters because they figure an extraterrestrial civilization that wants to communicate with us would realize that if somebody out there is listening and is advanced enough to want to do SETI, they would know about 21 centimeter radiation and would be looking at 21 centimeters, so let's send a signal to them at a wavelength that they're probably going to be monitoring, is what it comes down to. So that signal was seen at 21 centimeters. Now, whether it was, the death cries of an alien civilization, that's another matter, or a civilization saying hello or whatever, but yeah, it was seen at 21 centimeters as a matter of fact. So here is the spiral galaxy M83 seen in visible light, and here is the same galaxy at, what's that?
Will you change it to light?
I was trying to, all I didn't do anything. Yeah, let's try that. Here is M83 at 21 centimeters. So at 21 centimeters, it shows H1 clouds, clouds of neutral hydrogen. Notice that they are concentrated along the spiral arms of the galaxy. They're not quite oriented in the same rotation.
Tropical storm.
It does, yeah. It looks like a hurricane or a tropical storm on the radar. But yeah, H1 clouds are concentrated along a spiral galaxy's spiral arms. And here's 21 centimeters radiation from our own galaxy. 21 centimeter radiation, it's radio wavelengths, it can penetrate dust. So we can see clear across the galaxy at 21 centimeters radiation, at 21 centimeters. So you are here, here's the center of the galaxy. There's a shadow, if you will, here, not because the center of the galaxy is blocking the radiation, but because this material is moving transverse to our line of sight, so it doesn't show any Doppler shift. And it turns out you use the different Doppler shifts of clouds along the line of sight coupled with a model of the rotation curve of the galaxy in order to infer how far away they are from us. So we can see 21 centimeters from the other side of the galaxy through the galactic center, but we're not able to reliably say anything about how far away the clouds are from us, so that we just leave those data out. But in any case, you can see that in our galaxy too, the 21 centimeter radiation isn't uniformly distributed across the disk, it's preferential in the spiral arms. This is a way that we can make a rough map of the structure of our galaxy. This is a table, I don't know how we can read it from there, but this is a table of the components of the interstellar medium, and so we'll talk about each of those components here. So, where'd it go? And where's my chalk? What did I do with my chalk? Did you guys see what I did with my chalk? I can't function without my chalk holder. You didn't take it over to 130, did you? I don't think so. Wasn't I just now writing with it? Did I hide it under here? What did I do? This makes no sense at all. I was just writing it, right?
Yeah, you worked through 21 centimeters.
Right. What? Goblins, yeah. I don't think I'm going to check the tape as it were, although in principle I could do that. It's going.
That's all fine. Let's play find the chalk.
Yeah.
B, do you see it?
V, help us out here.
I'm just gonna walk around lost.
Yeah. V's like, yeah, it's right there. You guys are eventually going to see it. What's going
He's
on?
probably rewinding the video at this point to try
Yeah,
to figure out
trying to
when you
figure
set
out.
it down.
Yeah. This really makes no
He's
sense at
certainly
all. I was
laughing right
just
now at
using
it.
it, yes.
Found it.
Ah, very good.
Oh,
Okay, I put it in
Wow.
the chair, was that what it was?
Yeah.
You should
Ah,
have,
thank
when
you.
you found it, you
All
should
right.
have not said anything, so we could have kept playing Find the
All
Cover.
right,
for
yes.
another 10 minutes.
I see how much you're interested in this class.
Babe.
So. Some of that 21 centimeter radiation indicates the presence of so-called diffuse H1 clouds, all spread out. And temperatures on the order of 30 to 80 Kelvin. And number densities on the order of 100 to 800 per cubic centimeter. I could put it per cubic meter, but to me, 100 atoms per cubic centimeter means more than 10 to the 8th, I guess it would be, per cubic meter, right? A cubic meter is 10 to the 6th cubic centimeters. I can't picture what that means, but I can picture what 100 per cubic centimeter means. So I'm going to go ahead and keep it in per cubic centimeter for the number densities. All I have to do is divide by 10 to the 6th to get, or I mean, multiply by 10 to the 6th to get cubic meters, obviously. And the mass of the cloud is on the order of 1 to 100 solar masses. And
That's quite a range.
yeah, it is quite a range. Size is on the order of 50 to 150 parsecs. Also quite a range. And really, they're not like these nice spherical things. They're twisted into long filaments, flattened into thin sheets, tangled into chaotic shapes. This is gas in the interstellar medium, so it's not like it has well-defined boundaries. You're like, here's a cloud, here's not the cloud, with a sharp edge between it or anything like that. So, not spherical. Instead, twisted into long filaments. And flattened into thin sheets. And tangled into chaotic shapes. They're a mess. They're a hot mess. No, they're a cold mess. The intercloud medium is a hot mess, but these guys are a cold mess. And these guys seem to be about 25% of the ISM by mass. At least in our galaxy. It could be different in other spiral galaxies. But in our galaxy, they're about 25% of the ISM by mass. And then next up, we have the intercloud medium. Notice it's H2. It's ionized. It's much hotter, 1,000 to 10,000 Kelvin, and much lower density, more like 0.01 atoms per cubic centimeter. And nevertheless, it's in pressure equilibrium with the H1 clouds, and it can be in pressure equilibrium because remember that P is NKT, right? Number density times Boltzmann constant times temperature. What they lack in density, they make up for in temperature, so that they're pretty similar in pressure to the H1 clouds. And so as a result, it's a kind of fairly stable configuration. So between H1 clouds is the intercloud medium. pressure equilibrium with H1 clouds. And the intercloud medium is an important component. It makes up about 50% by mass of the ISM.
And that's H2.
Yeah. Yeah, so it's at least partially ionized. Partially ionized, look at the higher temperature means it would be partially ionized as a result of that. Move the camera so I can start writing over there. There you go, V. Why, thank you.
Is that your V impression?
That's my V impression, that's right, yes.
I wonder if V has a Dr. Harmon impression.
I don't know. I may not want to know.
He's probably rehearsing it right now.
Probably is, that's right, yes. Okay. So a dust cloud which becomes optically thick can shield its interior from ultraviolet photons, and that can allow molecular hydrogen to exist. So in these H1 clouds, you might have wondered, they didn't, but they're atomic hydrogen. Why don't they make hydrogen molecules? Because ultraviolet photons from distant stars can readily break apart hydrogen molecules. So for molecules to form, you need to have a cloud which is dense enough that the ultraviolet photons get absorbed before they can reach its center, and then in the center, molecules can form as a result of that. So UV photons from distant stars can dissociate H2 molecules an optically thick dust cloud can shield its center. Allowing molecules to exist. And in fact, the dust also enhances the formation of H2. Since dust grains can serve as singles bars. I said dust grains can serve as singles bars.
I thought you said.
Yes, I did. I was wondering if you'd be wondering if I really did say that. As single bars, in quotes. Idea is H atoms on the grains can find one another and combine. drain acting as a sink for the binding energy that gets released. Free atoms just zipping around, can be hard for them to combine with one another if they collide at high speed. But if they get stuck onto a grain, then they can approach one another at low speed and combine with one another. So it turns out that you'll get more hydrogen formed, more H2 formed with grains around than you would if the grains were not around. They enhance the formation. So not only does the dust absorb ultraviolet and protect them from being destroyed, dust also helps H2 molecules get formed in the first place. Kind of an interesting thought.
So this acts as a sink for the binding energy?
So in other words, the reason H2 forms in the first place is because an H2 molecule has lower energy than the two hydrogen molecules that form it. And so when they form, you have to release that binding energy, and they can just, the dust grain can basically heat up a little bit as a result of the binding energy that's released by the molecules forming. And it's much bigger than the molecules are, so it doesn't recoil much in terms of momentum. Right? If they combine, if they were to give off a photon, for example, there'd be momentum transfer. The grain would be able to take up any of that. So,
And that's a good thing?
yeah, it's a good thing. Yeah. The main thing is that they're able to beam on the grain at low velocity. That's the main thing here. It's kind of, oh, and by the way, the grain can take up binding energy. Yeah, that's more like, oh, and by the way, the grain can take up their binding energy. Now, this is something that I mentioned in E&M. If we want to study molecular clouds, far and away, the most common molecule in molecular clouds is H2, because H2 is H is most of the atoms, and so H2 is going to be the most common molecule. But H2 is terrible at emitting radio waves. Why is that? Do you remember? So you get an efficient way to create radiation is for the dipole moment of an object to oscillate. An oscillating dipole moment produces so-called electric dipole radiation. Will an H2 atom have an intrinsic dipole moment? No. No, because it's symmetric. The electrons are equally attracted to both ends of an H2 molecule. So it has no intrinsic dipole moment, and that means that spinning or vibrating doesn't change its dipole moment, so it's not very good at giving off dipole radiation. It's not very good at giving off radio waves. So in fact, to see molecular clouds, we observe other molecules, which are much less abundant, but which are polar. And a prominent one, for example, is CO, carbon monoxide. Carbon monoxide is not symmetric, it has a dipole moment. It's a much more efficient radio emitter. And so we, in fact, map molecular clouds from their CO emission, typically. We use other molecules too, but CO is a proper choice, is a popular choice. H2 is a poor radio emitter, so tracers like CO are used to map giant molecular clouds, which get shortened to GMCs a lot. Yes, question?
Why does the dipole radiation emit the radio?
Oh, well, so here we're talking about the quantum mechanics of it. The idea is that if you look at the energies of the vibration and rotational levels of the molecules, then, well, if you're looking at the rotational levels, they're in the radio typically. So, I think vibration typically, let's see, vibration levels are typically in the infrared, if I'm not mistaken. But the rotational levels are in the radio range. So, H2 is symmetric. No dipole moment. Not good radio emitter. So we use asymmetric. How do you spell asymmetric? 1S, right? Asym, 1S, 2S. So we use asymmetric molecules like CO as tracers to map giant molecular clouds. And for that matter, I mentioned the others, translucent molecular clouds. Although GMCs are what most of the actions that we're interested in. I don't feel like writing giant translucent molecular cloud yet. So TMCs. Form in denser regions of H1 clouds. So there we're talking temperatures of 15 to 50 Kelvin. I know this is exciting stuff when you get like these numbers like this. It's like, anyway. 15 to 50 Kelvin, and is about 500 to 5,000 molecules per cubic centimeter. Masses of about, quite a range, 3 to 100 solar masses. Whereas the really interesting ones, the GMCs, remember in the video, the Orion Nebula is a bubble in a GMC. GMCs are where star formation takes place. Giant molecular clouds contain star-forming regions. Temperature around 20 Kelvin. Number density around 100 to 300 per cubic centimeter. Mass as high as 1 million solar masses. So lots of raw material there. Range of size, but on the order of 50 parsecs. Thousands of GMCs are strung out along our galaxy's spiral arms.
So stars form at like 20 Kelvin?
Well, they're in clouds. They're regions. No, is the answer. Okay, but the GMCs in which star formation happens outside the star forming regions are around 20 Kelvin. So thousands of GMCs strung out along galaxies' spiral arms. I know it sounds like they're like they've been I've been doing too much.
Yeah.
That's true. So there where the action is in terms of star formation. And they make up about 25% of ISM by mass. It's about 100%, yes. But now, 5% is in the form of coronal gas.
The
Wait,
missing
what?
5%.
Yeah, the missing 5% is in the form of coronal gas. Wait, what? Well, it's because these are rough values. Coronal gas, hot stuff. So here we're talking T is around 100,000 to a million Kelvin. Number densities on the order of 10 to the minus 4, 10 to the minus 3 per cubic centimeter. Is highly ionized, must be given the temperature, highly ionized, and occupies as much as 80% of the ISM by volume. But only about 5% of the mass. And it seems to come from supernovae and hot star winds. Supernovae can blow high temperature bubbles in the interstellar medium.
Is this also from like the dredge ups?
No, it's just from the supernovas go boom and throw stuff out at 10,000 kilometers per second. Shock waves heat the surrounding ISM, and it's much denser behind the shock wave. They're blowing out bubbles, and so that's where the stuff is coming from. It originates in supernova explosions. And possibly hot star winds. Next time,